All right, why don't we go ahead and get started? All right, so good afternoon. Right after lunch, I have the opportunity to put everybody to sleep. My name is Dave Wickert. I'm a program manager with the Analysis Services team. We're the folks that bring you Power Pivot Analysis Services and the VertiPack engine, which is what we're going to talk about. One of the things that I love coming to conferences to talk about is that I love hearing what a little bit about you, and you get to learn a little bit about me. One of the things you may not know about me is that I am very much into amateur radio, ham radio, which is where it's a hobby where people communicate using radios. Are there any other ham radio operators in the room? Anybody? Oh, okay, what's your call sign? Okay, AE7TD. And from that, as you'll notice that it's right near my name. Okay, ham radio operators, our call signs uniquely identify us. And from that, you actually know a little bit about me. You may not realize that. AE is the international prefix for the United States. It's one of several different call sign designations for the United States. The 7 means that I'm in Area 7, which is the Pacific Northwest around Seattle. And TD just is TD. So you actually know a little bit about me. As I said, I'm into radios. This is my main radio that I use. I actually have like about 5 different radios. My wife thinks that I have way, way too many radios. I use an ICOM 7000 as my main rig. It's a 100-watt radio, which is kind of the medium of the range. I don't have a tower. I do not have a big antenna at my house. My wife won't let me, but I have a small portable antenna that I set up. It runs about 33 foot up into the air, and that's where I run my radio from. Radio is kind of interesting in that it's like flying an airplane. When I flew here from Seattle, when you look at the trajectory that the plane takes, the plane doesn't fly the way you think it flies. The plane flies in what's called a great circle. A great circle is the shortest distance between 2 points on the Earth. And from Seattle, they have this special map. This is called an azimuth map that allows you to point your antenna in a particular area to see where you would want to communicate with. Now, this is the azimuth map from the Seattle area pointing to the Netherlands. And as you can see, I have 2 major problems. And one of the reasons why I don't get a lot of contacts from the Netherlands and from Western Europe, from where I am in the United States, but I do get great contacts in the Pacific, even if they're farther away. It's easier for me to contact and talk to somebody in New Zealand or in Australia. I get to there all the time. South America I get to all the time, but I can't get to Western Europe. And the reason why is because, can anybody notice from this map the reason why I have problems talking to the Western Europe? What's the yellow area on that map? We're in the beginning of a sunspot cycle. What happens in a sunspot cycle? Is the sun starts, go ahead. Ionization of the atmosphere, which allows radio signals to bounce off of the ionosphere, and that's how we actually communicate. Because of the curvature of the Earth, radios don't let you do a direct communication except from the Earth to maybe satellites. But to have radio travel across the world, it can't go straight in a straight path. It has to bounce off the ionosphere. And the auroras, particularly on a bad sunspot cycle, disrupts all of that. And so one of the ways which ham radio operators learn to communicate is via Morse code. Have you folks ever heard of Morse code? Somebody's heard of SOS, the International Disaster Frequency. Well, this is what Morse code sounds like. I didn't think I had to run that into the amplifier system, because you can pretty much. Now, can everybody hear the tone? It's a 0 and a 1 tone. Sometimes a little long, sometimes a little bit short. Okay? Now this is great in theory. This is what it sounds like in reality. The reality is that there's a lot of noise in the atmosphere. And sometimes the signal is not quite as strong. Everybody still hear the tone? And sometimes there are people trying to communicate at the same time. Can you still hear that same tone? That's the cool thing about Morse code, is that tone, once your ears get adjusted to it, you can pick that out very, very easily. So to show that gets rid of all the other folks sending. There's a stronger signal. And then I turn the noise off. And that's one of the reasons why ham radio operators, even though everybody has a phone, we still use Morse code because it's a way to be able to communicate. Now, the cool thing about Morse code is it's a variable length encoding. In Morse code, depending on the strength of the characters, they have different signals. So E is dit, just a single, very short. And T is da, long. My call sign is actually a very good call sign for Morse code because it's AE7TD, which is da, dit, da, dit, which is a 7, da, dit. So it's very, very short call sign. Not everybody is as lucky as I. In fact, I picked out that call sign just because it's a nice signal. I have a radio on order. I told my wife the other day that I have this on order. She didn't know that. This is a KX3. It's like one of the latest, hottest radios that is coming out. The reason is because it is a QRP radio, which means it's very low power, but the receiver in it is absolutely marvelous. It's a world-class receiver. To be able to communicate with somebody, the first thing you have to be able to do is to hear them. Then you can have all the power to talk to them. But if you can't hear somebody, you can't communicate with them. And the KX3 is all about a quality, world-class receiver to be able to do that. So that's what ham radio operators used to have. That's not what we have anymore. Another thing that's big into ham radio is this notion of a software-defined radio, an SDR. I own one of these things. This is called a FunCube dongle, and it's a little USB device about that big. That you hook the antenna on one side and then you plug it into the USB port. What this is just enough hardware to take the radio signal and encode it in a digital format. Inside that is an A to D converter that takes the radio signal and converts it into a digital value, the same thing that's used on a cable TV. They actually use a cable TV encoder is what's in that chip. Everything else is done inside the radio. The FM demodulator, the signal processor, all of that is done inside the computer. And so you have this very advanced radio receiver and transmitter, but what it really is the computer. And the computer is doing all of the work. It's taking the radio signal and is actually doing the demodulation and cross-signal rejection, and everything else that's needed is actually being done in the radio. I have another radio, which is not really a radio. It's an encoder. So ham radio operators are also into voice over IP. This is a DV dongle, and what it does is it will take your mic and speaker system on your computer and do a hookup where you can do voice over IP to a repeater, which then takes it and puts that out onto the radio. So this is what my office looks like. I have an old laptop that's sitting there that's hooked up to a mic and some speakers, and you can see in the lower left-hand corner is that little blue DV dongle. And what that allows me to do is use the D-Star repeater system to be able to make a radio call. And I make an internet connection between my computer and my club station in Seattle, And that then takes that signal and transmits it out on the radio waves, which then allow me to talk in the general Seattle area out on the radio. And when I travel, I take that with me. I was on Sunday, I was on the air from my hotel room in Amsterdam here, talking to my club back in Seattle, Washington. So that's enough about me. Let's talk a little bit about you. So this is what this session is about. This session is about the analysis services engine when it's running in tabular mode. If this is the first time you've heard the word analysis services, you're in the wrong session. This is a 400-level presentation. We're going to be talking about the way which we do compression and the way we do bit encoding of the values, which we read them from the database. We're going to be doing lots of really wild stuff. If this is the first time you've heard the word tabular, if this is the first time you've heard the word power pivot, you are in the wrong session. You're more than welcome to stay and listen to the presentation, but you're not going to get an awful lot. If you're into analysis services, how many people are analysis services customers from here? Very, very good. How many people are power pivot customers? Excellent. Very, very good. Well, good percentage of the room's in the right place then. Okay. This is actually the second time we've ever talked about this. For the most part, a lot of these algorithms that I'm going to talk about, we have patents on, and we've just not been prepared to share. This talk was given at TechEd Orlando a couple weeks ago, and this is the second time this talk has been given. So this is the first time we've actually come clean and shared some of the technical details for the way the power pivot and the new tabular model work within analysis services. The reason why we're doing this is because we're getting bombarded with a lot of capacity planning questions. And what I'm trying to do, or what the objective of the course is, or this session, is to talk enough about the details that you get a flavor for what's happening, so that when you have to size a system, you at least can understand when the perfmon counters are talking about VertiPack scans, that you understand what those are and how they're being done. When you look and see that you have bursts in your CPU utilization when you're doing processing, that you can understand a little bit about what's happening in the background. And that's the purpose of this information, is because we're trying to get this information out so that folks can understand it for capacity planning purposes. Now, this is the full picture. I'm not going to go into this picture at all. What this presentation is about is just about that box, just about the VertiPack engine. We're not going to talk about direct query. We're not going to talk about MOLAP. We're not going to talk about anything else other than the VertiPack engine inside analysis services. We could do an entire talk, and there are several talks at this conference on DAX. We could give, if we wanted to, a separate presentation just on direct query, which is the new mode that analysis services has for directly querying a database at runtime, kind of like the ultimate version of real-time ROLAP. But we're not going to. This particular talk is strictly about the VertiPack engine and the way the VertiPack engine works internally. Okay. So when you think of VertiPack, there should be three things there are three key design issues that we focused on for VertiPack. Just from your gut, I show you this picture. What does this picture tell you? Give me words, word association. Speed, excellent, excellent. Some people have said expensive, which is not a good thing since we give away power pivot. Performance, 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 performance. This is going to be really driven as we go through this session. Many, many places in VertiPack, we were faced with compromises between whether or not we're going to do something for performance or whether or not we're going to do something for processing or some other kind of activity in the system. And every last cycle, we looked at every last cycle to see what we had to do to be able to. And so that's just a prime issue within VertiPack. Another word. This confused me too. I don't know what I didn't do these slides, so I have no responsibility for these slides. But so what this is attempting to show is that in any race, The vast bulk of the race is the race car out on the track, going as fast and as fast and as fast as it can. But there are specialized times, and if you know anything about racing, you know that when that race car comes into the pit stop, what looks like chaos in the pit stop is well orchestrated, very precision activities. They do split-second measurements to try to get the pit crew to work as efficiently as possible. But that's not what a race is. A race is about getting the car out on the track and having the race go have the race car go as quickly as it can. So while we recognize that processing and the other activities that analysis services has to do is important, our first criteria is performance, is query performance. Given a trade-off between query and processing, query wins. Everything in VertiPack is designed for speed. What else? Give me another word. This is the third one. This is the last association. I promise you, this is the last association test. Another word. James Bond. 2 words. James Bond. All right. So again, I didn't do this, but if you're going to fire those rockets, you have to reload the rockets. So one of the things that's associated with analysis services, as you know, is analysis services in MOLAP is very structured. What happens when you do a full process of a dimension? You have to reload all of your facts. And the reason is because in MOLAP, the MOLAP engine is very rigid. To be able to have aggregations work, aggregations forced us to make certain compromises around the way data is loaded and the way which we structure the data. VertiPack is the other side of the coin. VertiPack, we want to be able to have the data stream in as quickly as possible. We want to land it, and then we want to go on. So things like referential integrity constraints, we'll talk a little bit about that, not an issue in VertiPack. And we go out of our way to say that RI constraints is something that we don't worry about, and is something that where we do think about them, we think about it later on in the process. We want a system that is extremely flexible. In PowerPivot, when you import your data in from PowerPivot, that's like the last thing you got to do with it. You can drag measures down into the value field, and we create measures behind your back. We re-index things. You can create relationships on the fly. You didn't have to go back and re-import the data. So the flexibility for the data that's being imported, we want to be able to bring it in once and then not have to be able to worry about restructuring of the data. We don't want to reload the data. And that's a design principle all through VertiPack. So one of the ways which we get this performance through the system is through encoding. The first thing we do is we encode the data. When the data flows, when you do a processing of a table and you import the data into the VertiPack engine, the first thing we do is we encode everything. We don't keep the values as you give it to us. We encode everything. Everything is encoded. In MOLAP mode, we did some encoding. With other values, like measures, for example, we kept the measures as they were. In VertiPack, everything is encoded. So the first thing which we do is we encode the data. There's 2 primary encoding techniques that we use. Okay, well, the second step after we encode it is we then compress it. But the real key thing is the encoding. And there's 2 primary techniques that we do right today. We may do more in the future, but today we do value encoding and we do hash encoding. What's value encoding? What value encoding is it will look at the values as it flows in, and it will attempt to keep those values in place as they are. So, for example, you're importing some numbers. You have a quantity or a sales amount, and you're importing those numbers. Well, in MOLAP, we stored those numbers as those numbers were. In VertiPack, when we encode everything as they come, and even integers, we encode them. And we do sampling on the data, and we look to see whether or not we can compress integers as much as we compress strings and things like that, which we have for a while. The thing about values is that is what's good about values is you can do arithmetic operations on top of them. So you can do max, min, some statistical functions like arithmetic means and things like that. You can do on the integer data if you had it. But integer data can also be very wasteful. What happens if you had a column that only had two values? Highly repeating data, but it only had two values. It had a value 1 and it had a value of 1 billion. If this was an integer number, you would have to have 31 bits to be able to encode that, correct? Even though I only have two distinct values, I have to use 31 bits to encode it. I could have encoded it in 1 bit. So you're getting there's something that's happening behind the scenes. When we talk about a 50 to 1, 100 to 1 compression ratio with VertiPack, this is the kind of stuff that we're doing. And if we do have values that are very dense and very together, where we can do arithmetic operations on them, we try to do that. So let's give another example. Suppose I had 3 floating point values that had 3 distinct values. Had a number 1.5, 3.0, and 4.5. How should I encode those? Anybody notice a pattern? Well, number 1, it's base 15. Anybody notice base 15? Because those were floating point numbers, but if I scale them by 10 to make them to be 15, 30, and 45, then I have them be base 15. They're the numbers 1, 2, and 3. So if I created a dictionary that had the arithmetic scaling and base and put that away in a dictionary somewhere, and I had 2 bits, I could now encode that entire dimension and all of its values in 2 bits. Okay? And that's value encoding. Hash encoding is where we take the values and we create a hash table. And we convert the value from a string. A string is the canonical example, and we get great compression with strings. You take the string, you memoize it, you create an integer value for it, and then from there on, everything is based on that ID. We call that the data ID. That's grace for very spare distributions. So, for example, if you have long strings that contain addresses and things like that, hash encoding is very, very good. But if it is a numeric, it may require decompression to be able to do some kind of arithmetic operation on it. So it's not always the perfect thing to do, because the value that you're putting into the table is the data ID, is the encoded value, and if it doesn't have any bearing with the original data, you've got to decompress the original data to be able to get the information back. So here's 2 examples. As we talked about, let's say you had 2 billion and a number 1. Would you use hash encoding? You probably would, because you don't want to use all 31 bits. So for these 2 values, you could hash encode the values and get that wide dispersed data. But if the numbers were very dense, then you would use value encoding with it. And the engine does this automatically. So another design principle for VertiPack is we don't give you a lot of knobs to be able to switch and change. So we could give you a property that you set on every table that says use this compression algorithm, or force the engine to use this type of encoding. We don't do that. What we do is we use sampling. We'll read the first 200,000 rows in a table. From that distribution, we'll decide what kind of encoding to be able to use. And all of that information. So in general, we don't make this information be a knob that you can turn. But we do make the information available to you in the fact that it's exposed through a DMV. So you can query the system, and I'll show you that in a little bit. So what actually is happening when you process a dimension? What is VertiPack? Number 1, VertiPack is a column-oriented data store, which means that unlike SQL Server, the relational database, that if you look at its low-level page formatting, you'll see that it's a row of data, a row of data, a row of data. SQL Server is a row-oriented data store. VertiPack is a column-oriented data store, and what we do is we read in a row of data from the relational source, and we pull out all of the column information, and we take for all of the rows, we pull out what its column information is, and we store those together in a part of the database. And then we go to another column, and we store the other column, and then we store another column. So the row is spread out all over memory, but the columns are concentrated together. So this allows us, when you do a group by or you do a select clause, how we can do the data is very central, is very is co-located together. In fact, we can do table scans very, very quick because it's a column-oriented store. It means that it's very difficult for us to delete a row of data. So when I talk about partitioning, we'll talk about the trade-offs that we're going through here. It's difficult in VertiPack to delete an individual row, but adding and deleting columns is a piece of cake because those are handled directly. So the first thing we do is we encode all of the data as it flows into the system. And when we encode it, we create two different kinds of things. We create the column values themselves, which are stored in segments, and we create this dictionary. So remember, we went through this encoding. The result of the encoding is a dictionary that says either what the formula is that you use for the value encoding, or it's the dictionary itself, which is the hash table, and then the data itself is the data IDs in a compressed format. So what's in the column-oriented store is not the original source data, it's the data IDs. It's the encoded values is what we're then compressing. So in the core underlying data, when you do a process data, is the core data as a column-oriented, encoded dictionary and segment. And that's what's kept around. When you do processing, that's the core data element that's being stored. Then we have a series of ancillary structures that we keep for a table. The first is calculated columns. Unlike SQL Server that creates calculated columns as calculations, in VertiPack we materialize everything. So when you create a calculated column, we will actually create an actual data structure that is a materialized view in relational terms, which is the materialized column for that calculation. And the reason why we do that is performance, performance, performance. Because we're not doing a complicated calculation at runtime. We want that data right there to give you split-second, sub-second response time. We also create hierarchies. So if you have a denormalized table where you have the product subcategory, and the product category all in the same table as a hierarchy, it's kind of a drill down path for a hierarchy, we will create indexes associated with those fields and store that inside the table. And we also keep relationships. Relationships are foreign key referential integrity constraints between tables. And so we will create a structure where if you have a foreign key lookup between tables, if you have a star schema where the fact table have got foreign keys in them that point to the dimension tables, or if you have a snowflake schema where the various levels are broken out as separate tables, then we will create a relationship materialized index for you. But that's kept as a separate object. So when you create and delete relationships in VertiPack, we don't touch the original data. We don't touch the hierarchies. We don't touch the calculated columns. What we regenerate is just the lookup tables between the foreign key constraints for the relationships. And that's how you can add relationships and delete relationships in Power Pivot and in VertiPack without impacting as much of the underlying data. Also, just like a relational engine, you are not required to have relationships set up. If you use left outer or right outer joins between tables, and you specify the key values between them, we will do the normal things you would expect in a relational database to do, where you take the values from the left outer join and you pull those values and you push them down into the larger fact table to be able to do a selection. The same thing as what if you know what a star schema optimization is in relational database terms, we'll do the same thing here. So relationships are optional in Power Pivot. And if you want to do an ad hoc join, if you form the join through a calculated column, then where you don't have the relationships in place, and you're using a DAX function to be able to do the code lookups, because you don't have any referential integrity constraint, and you're doing that inside either a calculated column, then those lookups are perfectly fine, and we'll use those. We also partition the data. Now, today, partitions do not keep statistics. So unlike MOLAP, where MOLAP keeps cardinality counts for all the partitions, and it does that so when it creates aggregates, it knows how to create what the right level of aggregates are and knows what the right size that the aggregate will be. It needs statistics to be able to do that. In VertiPack, we don't keep aggregates. VertiPack does not keep aggregates. Right now, there are no aggregates on our plate at all for VertiPack. And the reason why is because aggregates force you into a rigid structure. And we don't want to do that. Maybe sometime in the future, but not right now. We don't keep aggregates. One of the purposes for why the engine is so blazingly fast is because we don't want to keep aggregates. The engine is so quick that it is faster to do scans of the underlying data than it is to read the aggregates from disk. Disk access today is so slow, particularly if you're going to real disks, is so slow compared to the CPU speed that VertiPack as an in-memory engine can do table scans, as we'll look in a little bit, in the billions and billions of rows a second. And that's on a laptop. That's on this laptop. On a server, I can do tens of billions of rows a second. It's quicker for me to do max via a bubble sort than it is for me to keep an index that has you walk through a B-tree index to have you do a max. So VertiPack, you'll see us talking about VertiPack scans, and the reason why we're doing that is because we're going down to the raw underlying data, and the engine is so quick and is so structured to be able to do that we can do that. All right, good. So today, partitions exist only to be able to do data management. It's a fast way of doing deletes. Deletes in the MOLAP world was kind of a benefit that people use partitioning. Well, I could do partitioning and I could keep a rolling 60 months worth of data. I could delete my partitions and thus have a rolling 60 months worth of time. That was kind of an ancillary reason why you had partitions. The main reason why you had partitions was to be able to do aggregates and be able to cut down the amount of data that you had to scan through. For doing partitioning. It was for query patterns. It wasn't for data management. Data management was kind of a side benefit of partitions. The main reason why partitions exist in MOLAP is for query performance. In VertiPack, our scan rates are so quick, we don't need aggregates. We don't need partitions for that. We do need it for management. So today, we don't keep statistics on partitions. We just use it for management. So you can do it we use partitions for bulk deletes. So how can you look at this information? So let's kind of show you some tools. All right. That was the Morse code simulator, by the way. All right. So how many people know what DMVs are? DMVs? Okay, good. All right. Well, there are some specialized DMVs for VertiPack that give you some of this information that we've just been talking about. There's the poor man's way of doing things, and then there's the DMV way of doing things. The poor man's way of doing things is the way we've done this with PowerPivot for a while, because these DMVs don't work against PowerPivot, but because of the type of engine that PowerPivot uses, or the fact that PowerPivot is so workbook oriented as compared to database oriented the way VertiPack is. So in VertiPack, since the databases exist independent of the workbook, you have things like this. So here you have a DMV. You can create a discover storage tables. It will give you cardinality counts. It will also give you whether or not you have any RI violations. We will talk about that in a little bit. So sometimes you see us do a demo. If you've seen any one of our keynotes where we had this 2 billion row sub-second movie recommendation database that you've seen Amir Nets give demos on and things like that. And that's this database. It's about a 10 gig database. Once it's all compressed, it contains about 2 billion rows worth of data, and you have a DMV that you can query, and it'll give you a row count, 2 billion. And then there's another DMV, discover storage table columns, which will give you all of the columns oriented with that table. And as you can see here, along with the data types, we also give you the column encoding. So if you want to find out, now we don't give you a way of influencing whether or not something is hash encoded or is value encoded, although I'll show you in a minute how you can look to see what the sizes are that are associated with those. But you can detect whether or not what kind of encoding it uses. And that is, there's a field here called column encoding. It's a 1 or a 2 that says what kind of encoding format we're using. And one of the things you'll notice as you look down through this is that wherever you see value encoding of a 8-byte, of an I8, an integer that's being used for 8 bytes, which means it's a double long word data type, like the ID, these IDs here, I can tell you that since those are value encoded, it means they were very small. They were very dense codes. They were things like department ID. Maybe they had a couple of hundred values and they were integers between 1 and 100 or something like that. Okay? If you see an integer that has a hash coding, so there's a date ID. You notice this one here is an ID. It's also an 8-byte integer, but it uses a hash encoding. Well, why is that? Probably because we have such a large, it was probably a fact table that has such a large number of individual dates. It has a high enough cardinality that the VertiPack engine said, no, I can't use value encoding. I need to be able to use hash encoding. And it switched to using a hash encode. So you can't, from the data type, automatically assume that something is hash encoded or value encoded. You have to go to the DMV. And there's another data item that we have here, which is for each one of the segments. So you can come into the DMV and look to see for each of the various columns what the cardinality count is and what the allocated size is. So here you can see that for the 5 gig, or I guess what, maybe 8 gig total for this database, 8.5 gig total. The vast bulk of it was time and was user ID. So these were high cardinality fields. They were probably hash encoded, and the vast percentage of the data is being stored there. So there's 2 things you should be asking yourself when you see this kind of field, this kind of allocation in your database. The first is, do you really need user ID? Are you really doing analysis on user ID? Maybe, but you're also unlikely to. User ID is not typically something that you're doing analysis on. Time. If you have a high cardinality value like this, it probably means that this is a date timestamp, in which case you are keeping a down to the millisecond individual timestamp for that particular field. Is that really what you're going to do analysis on? What would happen if I took that field and I made it a time or a date-oriented data type? I still, even if I wanted to keep it as a full date timestamp, but I got rid of the time part and I had just had it be the date. What happens to the cardinality of that field? It goes way, way down, because now rather than individual timestamps, very high cardinality, very unique for each row, now I keep it down to the day and the total, and I get a lot of repeating columns, which means that I can do compression. I still have to use hash encoding, but I can start compressing those because they're no longer individual values. And I'll find that a column like that will start shrinking considerably if I was to do that. And that's the way which you play with space allocation. That's how you can take a database that you would think, if you look on the relational side, is taking 300 gig and compress it in a VertiPack engine down to 1 gig. We have, depending on what kind of analysis you're doing, do you need all the fields? That's the first question. Do you need all the fields, all the columns? And the second question is there a way which you can take a high cardinality column that you are doing analysis on and change the semantics on the relational side, maybe by loading through a view and converting date timestamps to be just dates, and give you the same analysis for what you needed to be able to do, but make them be more of a repeating group. As soon as you make them more repeating, then the compression algorithm becomes more effective, the total size goes smaller, and the amount of the size database that you can put on one server becomes a lot more doable. And that's how you take a very, very large database and you map it into an in-memory database that you say, hey, there's no way I could do this with SQL Server. SQL Server, I got a 30 terabyte database. There's just no way I can take this database and put it into VertiPack. You know? There are ways, and that's the kind of some of the tricks that you can do. All right, processing. So this is a we did a little bit of a run. This is a 24 million row table that was being processed, and it's processed in a series of phases. You'll see that there's these long runs where you have the CPU is this is a 4-core system. So you can see in the beginning, there's 1 core being used. It jumps up to like about 3 cores, and then it drops back down to 1 core. So we're going to kind of go through what's happening here. You'll notice that in the beginning, memory utilization is high, and it increases over time. And then we kick into a high CPU phase. Memory utilization stays relatively flat, still high, and then we drop down into another phase where memory utilization kind of backs down and CPU utilization kind of also backs down. We kind of go along for a little bit, and then we finish. So what's happening here? We're going to skip that. Okay. First thing is, as I said, is we encode the data. So what we do is this is a single-threaded process. We go out, we execute the SQL command, we pull the data in. And this is just like MOLAP. We're pulling the data in row by row by row by row by row. And we're encoding it, we're building our dictionary, and we're putting it into the segments as the data flows in. And this is a single-threaded operation for a particular table. I could have multiple tables happening at the same time, but for a table, this is a single-threaded operation. Then, once I have all the data in, then I can start compressing it. So then what happens is I start up a separate job to do the compression, and the next segment starts reading in the values. So what you have is you have this shift. You kind of shift from first gear into second gear, where you're starting to be more parallelized, and you're doing your compression at the same time as you're reading the next segment. And then you finish with the compression there, and you go on to the next block, and you just continue this cycle as you're reading data in. Then once you get all the data in and that the core data structures have been built, then you go in and you calculate calculated columns, you calculate your hierarchies, you calculate your relationships, and you fill in all of the other different data structures. And that was that tail at the end of the CPU cycle. Now, VertiPack is performance, performance, performance. This is one of the optimizations. Now, in VertiPack, the default segment size is 8 million, which means that for Power Pivot it's 1 million, but for VertiPack, for the core engine, it's 8 million, which means we read in 8 million rows and put that into a segment, and then we read the next 8 million, and then we read the next 8 million, and those are put in segments. One of the things we wanted to do is we wanted to have more numbers of rows that could fit in that first segment, because there's a lot of dimension tables out there that are under 8 million, and there's a lot of dimension tables that are between 8 million and 16 million. It's kind of unusual to go above 16 million. But we wanted to keep the segment size be variable for the first segment. So this is, unlike the other diagram, which talked about n and n plus 1, this diagram only talks about the first and the second segment. It says that for the first and second segment, I will stretch it to go up to 16 million. I will start reading the segment in. If it's more than 8 million, I'll keep going because I really want to put everything into one segment, because then I don't have to indexes and do different hops to be able to do lookups and worry about the CPU cycles later on. And I'll do that up to 16 million. If I cross the 16 million threshold, I'll say, no, that's too much. I've got to go to this additional indexing for the multiple segments. And I'll take those 18 million and I'll split it into two, and I'll go back to my 2 million or my 8 million in a segment. So what happens is, just for the first segment, we start reading, we fill in 2 segments worth of data. If there's still more data, we stop, we split the segment into 2, we do the compression at the same time. That's why the CPU went to 3. That's why the CPU utilization jumped to 3. 1 to do the read ahead and 2 to do the processing for the first segment. And then I'll continue on. And I'm doing this work only because I want to be able to have a variable first segment, so that for some dimension tables and other tables that are between 8 million and 16 million, I want to have the 8 million performance at a 16 million size. That's the kind of tricks that we do to try to keep the performance up. And that's what's happening here. You'll see the first phase, data is being read in, memory utilization is going up and up. As you're encoding, as you're generating more segments, it's going up, it's going up. Then you're filling up that segment, you're shifting into the next phase. The first ramp up was segment 1 and segment 2. That's why CPU utilization jumped up to 3 CPUs. If this had been a larger table, and I was on the 5th, 6th, or 7th segment, I wouldn't see 3, I would see 2, because I'm just 1 behind. But for the first one, I'll see 3. And that's what's happening under the tables. So I see segment 1 and 2, then I do a split where I generate the segments back down to 8 million. Then I'll start up 3 CPUs in parallel, compress the third, generate at the tail end, I'll generate my calculated columns, relationships, and hierarchies, and I'm done. So the 2 knobs that we give you, the first knob is the segment size. Today, this is kept as a server property. You can go in and change. The default value is -1, and -1 means that it depends on how the engine is running. If the engine has been started in Power Pivot mode, it's 1 million. If the engine has been started in VertiPack mode, it defaults to 8 million. If it's something other than -1, like 8 million. It has to be a property, it has to be a power of 2. Who wants to make a guess for why it has to be a power of 2? Speed, speed, speed. We're doing bit shifting here. So we have to be a power of 2 because it's faster for us to do bit shifting than it is for us to do arithmetic calculations. But you can adjust the segment size if you want to. If you have a very, very large table, if you came to me and you said, Dave, I need to build I have a source table that is a terabyte, and I need to load that into VertiPack. I want to get the best compression, and how do I do that? First thing you'd say is go to your segment size. Your segment size probably has to be triple or 4 or 8 times larger than what the default value is. Larger segment sizes means you get better compression because repeating groups can be handled in one value inside the segment. So you get better repeating groups and better compression within a larger segment. You actually get better control over CPU processing or CPU handling at query time because we parallelize the query based on the segment. So when you need to do a VertiPack scan, if you have 10 segments, we will spin up 10 execution threads to be able to scan those 10 segments in parallel at the same time. If you had 1,000 segments, we potentially could try to spin up 1,000 threads, which no single CPU can handle today, and you'll get these massive CPU spikes. So segment size for a large database, you want to keep the segments large even because they give you better scheduling. Every single time you spin up a new thread, that requires us to schedule it, tear it up, tear it down. So you want the segment size to kind of match where your numbers of CPUs are. But the smaller segment size, and the reason why PowerPivot is started with 1 million is because PowerPivot is very sensitive because it lives inside the Excel process. In PowerPivot, when we load in memory with Excel, in PowerPivot for Excel, we are in the Excel memory space, which means we can't go allocating large working sets. So in PowerPivot, the default segment size is 1 million rows. To try to keep our memory utilization down, we're willing to have the CPU spikes because Excel tolerates those better than the memory. Plus, the data sizes that people deal with Excel, they're not in the 5 and 10 terabyte range. They're in the hundreds of megabyte. They're in the 1 or 2 gigabyte range that you can do with Excel. The other knob we give you is with the compression algorithm. Now, if you went to Knuth, you would probably find, what am I talking about? Knuth, there's a significant part of his books that talk about sorting and compression algorithms. I mean, everybody and his uncle has got patents these days for compression algorithms. We handle a good 24 different types of compression algorithms. And what we do is we have this greedy algorithm that kind of starts with the ones that we know are the most efficient and compress the best, and we try those out first. We do a statistical scan of the first 200,000 rows in the table, and we try to figure out what's the right compression technique to be able to use. And it's a greedy algorithm in the fact that it's very CPU intensive. It tries to get the benefit, the bang for the buck, as early in the process as it can. And so what we do is we time box it. We say, when we start the compression algorithm, how much time are you willing to have the system pick the best compression algorithm? And you can control what that time box is. So the default is 10 seconds, which means that we will sample the database and we will try to figure out the compression algorithm on a large segment for 10 seconds. After 10 seconds, whatever is the best algorithm that we think, that's what we use. Now, if you had a large segment, if you had bumped your segment size up to 64 million rows, went up by 8, then you probably would want to also change the time box time because you want to spend more time on a larger segment before the compression algorithm decides on exactly what it wants to do. There's no no perfect number for the time box. It's very data dependent. So our general recommendation right now is to give you the knob, and you're going to have to run experiments on your own data. This is only going to be relevant, I think, if you're going to adjust the segment size. But if you're going to run large segment sizes, you probably will want to adjust this knob at the same time. So when you process, you can do process data. This is the same thing as you get with analysis services today, where we just read in the data. We don't generate any of the ancillary structures. We just read in the column store, and we do the encoding. And that's all what you do. We also give you the option to recalc. What recalc does is it goes away and it calculates just the calculated columns, the hierarchies, and the relationship structures that have to be done. And so we will give you the separate processing command to be able to do that. The reason why we give that to you is because if you're processing a large data set, it's better to do process data, process data, process data, process data, and then a recalc than it is to process a partition, recalc, process a partition, recalc, process a partition, and recalc. Because the recalc can actually be pretty significant based on the relationships and the calculated columns that you've defined for your table. So we give you some processing control over how you're going to do your data. Recalc also, because it deals with relationships, recalc is done at the database level. It's not done at the table or the segment level. You can't say recalc just this table. You recalc the database, in which case because the table could have relationships, we don't know that beforehand until we actually do the recalc command. So that's why you're going to want to do data, 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 and then a recalc at the end. If you got a small database, you're doing an initial thing, initial load. You can do full and do it all in one process command if you want to. We also have an option called default, in which case we know whether or not recalc has been happened or not, and we will do a recalc if you didn't do one before, and we'll bring it all up to the equivalent of processed full. We also have something called defrag. You'll notice that when I was encoding, when I was building that dictionary, nowhere did I mention the word deletes. Right? The algorithm, the data flows in, you build the directory, you do your encoding. Nobody mentioned anything about deletes. Deletes are not in the picture. What happens when you have partitions that you delete you do a bulk delete, you delete old partitions, what happens to the dictionary? For performance reasons, we leave the information in the dictionary. Over time, your dictionary can have a lot of zombies, meaning that they exist in the dictionary, but there's no data, because you deleted the partitions that contain all of that data. But we didn't clean up the dictionary, so the dictionaries, the lookups, still exist. Defrag goes back through the column-oriented store and rebuilds the dictionary for that particular table. It's really only useful for when you're doing partitioning. And we give you process clear, which just blows away the structures so you can rebuild everything from scratch. You'll notice that there's no aggregation. Again, I've stressed there's no aggregations here. VertiPack is strictly a column-oriented tabular structure. At the storage level, there's no notion of dimensions. There's that's something the formula engine layers on top of the storage engine. The VertiPack storage engine is a tabular-only data structure. It only understands select, project, group bys, and the general where clause formulas. And but we do have process add. And process add does the same thing that we do in the MOLAP side, where we generate a temporary partition, we process that partition, and then we merge it back in. So if you're going to do incremental processing, and I say that this is incremental processing for a table, not for a dimensions, because you can have partitioning of dimension tables too in VertiPack, because VertiPack is a tabular structure. It doesn't differentiate between whether or not something is a fact table or a dimension table. So you can partition a dimension table if you want to. Multidimensional is something that the formula engine layers on top of VertiPack. If you're going to need to create new partitions worth of data, you create the partition, you do a process data, you load it, you load it, you load it, then you do recalc. If you do delete, 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 where you're deleting partitions, then you may want to go back and do a defrag. But the one thing that you don't want to do is a process full or a process default on an individual partition individual partition partition by partition by partition. So, for example, if you partitioned weekly and you were at the end of the month and you wanted to have 4 partitions that were processed, you would not go in and do a process full for each week's partition. You should do a process data for each of the 4 weeks and then do a process recalc for the month. Parallel processing. The engine natively supports parallel processing. And the same technique that you used in the MOLAP world with the coordinator execution mode and the max parallel in your XMLA scripts, same thing happens in VertiPack. We do full parallel processing, except for partitions, meaning that when you are processing a table and you're processing 2 partitions in a table, the engine automatically throttles back so that it will only process 1 partition at a time. We didn't want to do this. It was purely a matter of resources to get the product out the door. We do not partition within a process, or we do not process within a partition. So you cannot be processing multiple partitions for a table at the same time. You can be doing multiple partitions in different tables at the same time. But for a table, you cannot process 2 partitions at the same time. The engine automatically throttles back and will make that a single-threaded operation. Just like in MOLAP, you want to do partition merging to keep the number of partitions as small as possible. VertiPack does not solve the analysis services metadata issues. We still, in VertiPack, just like in MOLAP, prefer to have a system that's in the hundreds to very low thousands of partitions. Analysis services is not the product if you think you're going to generate 100,000 partitions, if you've ever tried to do that in analysis services. And VertiPack doesn't solve that. It still is very sensitive to very large amounts of metadata. So you're going to want to keep the metadata as small as possible by merging partitions. But one of the places where we are very different is the way which we do RI referential integrity constraints. So in MOLAP, where you have a missing dimension key, you're processing a partition, a fact table partition in your fact table. What happens if you have a missing code lookup for your dimension table? By default, unless you've created an unknown member, the system stops and gives you an error message because we force the system to have referential integrity constraint. In VertiPack, we automatically generate unknown members. They're blank. We use the same semantics that Excel does, and we just keep driving on. So data is always read in, even if there are referential integrity constraints that have been violated. We bring the data in. We process the relationships, and if there is RI constraints, then we will assign them to the unknown member automatically. Which means that in VertiPack, because of the way the recalc is done, it makes no difference what order you process your database in. You can process your facts and then process your dimensions later on, no problem. Now, in MOLAP, you can't do that. In MOLAP, you've got to process all your dimensions first, and then you process your fact tables. In VertiPack, you don't need to do that. That's because when we recalc the structures, that you've added the relationships between the tables, that's when it's built. It's built at recalc time. It's not done during that initial encoding phase where the data is brought in. It's just that relationship between the two tables that's built, and that's built when you recalc. Okay, so there's a cost through all of this, and the cost is memory utilization. So VertiPack is an in-memory database, and the first requirement is that all databases have to fit in memory. All databases have to fit in memory. So you must have enough physical memory on your server to be able to load all of your databases. Not necessarily all of the uncompressed, but all the compressed data structures. That core data structure that we talked about has to be loaded in memory. We also have a formula engine, and there is a fair amount of caching that's kept at the formula engine level, and that memory has to be done. We also keep a cache between the formula engine and the storage engine. So the way analysis services works, I'll show you in a minute a picture of this. At the top, below, as your queries come into the system, as they come through the front door, the first thing they talk to is the formula engine. In the formula engine, there's two types. There's DAX and there's MDX. For DAX, which is what VertiPack is built on, the formula engine understands all complex calculations in DAX and attempts to, as much as possible, take those operations that the formula engine wants to do and push it down into the storage engine. The VertiPack storage engine sits down underneath the formula engine. There's a cache layer that's kept between those two so that at any point in time, if the formula engine wants to keep asking the same query to the storage engine, it does. And then there's a cache between the two that says, I already answered that question, formula engine, here's the number. So we need some memory to be able to do that. So there is a cache that's kept on top of VertiPack for the formula engine, so the formula engine can re-ask the same queries over and over again of the storage engine if it wants to. And if you're going to do processing, and we all have to do processing at some point in time, we have to have enough memory to keep the uncompressed data if you're going to do things in a consistent transaction where you need to be able to keep the old data available and querying while you're processing the new data. You got to have enough physical memory for both databases before the commit happens. Okay? So depending on your usage of the system, if you do a process clear and you clear out all the structures before you reprocess, let's say you're on a dedicated processing server, then you don't need to have 2 copies of the database. But if you're going to do processing on your live server, where you need the old database there so that people can continue to query it while you're doing process for the next version, there's no free lunch. You've got to have enough memory for both copies of the database until the transaction is committed, in which case we'll flip the databases back around and the old database will disappear. Okay, so depending on how you're using your system, you may need enough memory for a whole nother copy of the database. This is true with MOLAP, by the way. It's just that in MOLAP, we didn't force the entire database to be in memory. We forced you to just to have the data cache in MOLAP in memory. In VertiPack, you're required to keep the whole database in memory. We have 2 knobs that you can adjust. There's a server property called the VertiPack memory limit, which by default is set at the 60% of your physical memory on the machine. And we have high memory limit, which is set at 80% of the physical memory of the machine. Those are the default values. If you want to trim them back, you're free to. And we do have a paging algorithm, but be very careful here. Paging, as we've implemented it today, is only designed for processing so that we can keep the system running and processing without giving you out-of-memory errors. Namely, as you are processing, there's a whole bunch of buffers that you're leaving behind, like uncompressed memory, and as you're doing transactions, the committed memory that may have already been written to disk. So we're keeping track of that, and that information can be paged out. So we will try as much as possible within a processing command to give good memory utilization so that you don't run out of memory. And within processing, we will page out portions of the memory if we no longer need it for that processing command. But at the heart of it, we're still an in-memory system. We do not page out direct dictionaries. We do not page out segments that have been committed. All of that information has to be in physical memory at the time. The only reason why we have paging is to be able to allow you to do processing on a kind of marginal memory system. By default, paging is turned on. If it was my server and I wanted to know when I'm starting to run out of memory, if I'm writing on the edge, I would turn off the paging algorithm. It's a server property, you can, because I want to get my out of memory error indications early in the process. But if you had a server that you were running right on the edge, then keep the value the way it is and page out your memory during processing. But be very careful. You're going to get very unpredictable query results if we ever start having to page out memory, because Vertipack is an in-memory system. Okay. As I said, this is the diagram that I just drew for you, where there's two different formula engines on top of the Vertipack engine. This is our scan rates. This is what we can, I mean, I'm in a public forum and I'm talking about billions of rows a second, and this is what you can do on a laptop. And this is what you can do on a server. Again, just what does it mean to have a system where you can process 10 billion rows a second in throughput on a server class machine? It means that the algorithms can be totally reworked, and things that are just inefficient to do, like max over bubble sorts, things that we haven't done in years and years and years. Way back in the old IBM days did we use some of these algorithms. It's actually more efficient to do that at Vertipack because of the scan rates, because we can take the scan rates and line them up with the CPU caches so that on the new NUMA hardware architectures, we can get efficient scanning through memory because of all of the cache rates that the newer CPUs give you. I do want to show you what happens when you query the system. So here, let's go to a system. Let's do some things. First of all, I want to show you with the caches cleared. So I will clear my caches. Standard XMLA commands, just like you would clear your caches in MOLAP. I have SQL Profiler running. I'll make a connection to my server. I want to change some of the default settings because the default query processing, again, for performance reasons, we don't normally turn these things on. I'm going to turn them on to you for you to show that you see that these are happening. But these are profiler events that will tell you when the Vertipack scan engine is being kicked in and how long it takes for the individual queries. So if it ends with Vertipack, you should turn them on if you want to see this. So let's get this running. We'll clear it. We'll come over here. We'll clear it. So here I have, let me just do this. So here I have Excel, and I'm just going to query. This is a 4 million row Contosa sample database. It's pretty small. It runs in 150, 200 meg of memory. So I just did a subtotal scan. You see you get that kind of split-second response time through the system. And if I go back and look at Profiler, this is where I'm starting to see some things. So here, let me stop it. So here's a Vertipack query. You'll notice on the bottom, looks like SQL. You'll notice, remember I said Vertipack does selection, projection, group bys, and joins. So you look at that, those are left outer joins from a single table. with sum, count, very simple calculations on the projection, and only particular columns on the projection. And that's what VertiPack executes. That's the kind of query. It's a very, very simple relational tabular structure that VertiPack is going to run. Okay, and that's how you look at it. And if you can come across, if you want to, and look at the profiler duration events, and look at the CPU time, and you can look and you can see how much time is being spent in the VertiPack execution engine and how much is happening in the formula engine for the overall query. So the real trade-off in VertiPack and analysis services is DAX versus VertiPack. DAX is a very rich, expressive calculation engine that can do all kinds of things by calling down into the VertiPack over and over and over again. But VertiPack itself is very small, very simple, very, very fast. And more, as we're doing the differences between PowerPivot 2008 R2 and 2012 and future versions, we'll be taking more and more of the DAX functionality and trying to push that down into the raw engine inside VertiPack. And the reason why is this is Amdau's law that talks about how you can calculate the maximum speed up for parallelizing. Basically, the notion is that any query execution, no matter how much you parallelize it, there's some operation that is sequential even in a parallelized query. So in a parallelized query, maybe you have to read things from the disk. Maybe there's some kind of operations that have to be done sequentially. And no matter how much you parallelize it, so here the various color for the lines there says what percentage of the operation can be parallelized. So you look at, so if 50% of the operation can be parallelized, even if that became infinitesimal and you were left with just the sequential, you only have a speed up of 2. Go to 95%. Let's say that 95% of your system could be parallelized and you could optimize the heck out of it. And only 5% was sequential. That means the maximum speed up that you could ever have is only 20 times x. So ultimately, in any large high-performance system, you have to get something that's blazingly fast for the sequential part of the system. And that's why VertiPack was designed from the ground up. VertiPack did not start from MOLAP. Brand new code base, brand new engine, brand new assumptions. It was designed for blindingly fast speed. And that's the reason why, because we need that fast sequential operation to be able to get long-term performance out of the system. Performance. So we looked at the architecture of the overall system. We looked at processing and the relationship between querying and processing and the kind of steps the processing has to go through. And we looked at the query architecture as far as the way the system uses that information and how you can get the query times to see when things are happening inside VertiPack and when they're being done in the formula engine and other components in the system. And with that, hopefully you can use that for capacity planning. Please fill out your evals. I'll be around all week. So there you go. Thank you very much.